Okay, let's continue on the triple integral here, okay? So whoever here is in the class today, you're my hero. This is really bad. Yeah. Okay, so triple integral, I finished the Cartesian coordinates, and let's continue on the cylindrical coordinates. Cylindrical coordinates, it's very similar to polar, except that you added one dimension. Basically, to describe this point P, we can describe that using either x, y, z, or using another set of variable, which is r theta z. As we can see, the r theta is basically like the same as a polar, because x equal to r cosine theta, y equal to r sine theta, and z is still the z. Okay. This is the relationship. It's basically between x, y, z and r theta z added here. Okay. Now, often in time, you may describe things using polar coordinate. For example, let's say you say, okay, I wanted to describe this thing as, let's see, r equal to a. Okay, so you're talking about something using polar coordinates, and you see you give people r equal to a. So very similar, like you give people saying, okay, what's x equal to 2, right? So you can tell people x equal to 2. When you see x equal to 2, and in 3D sense, you're basically talking about it's a plane, right? You know, it's a vertical plane, x equal to 2. So what about in cylindrical? If you tell people, okay, here is something r equal to a, what do you think that represents? In 3D space, r equal to a in planar case is a circle, right? But in 3D, it's actually represent cylinder. Okay, so that's basically something that you had to be cautious now, because this is in 3D. For example, now you see, if you see that theta equal to a constant angle, what do you think that represents now in 3D space? It's a plane, right? Theta, this is theta here. When theta is constant angle here, basically you're talking about it's a reading line here with a constant angle, and extend that line here, so you basically get a plane. Okay, yeah. So that's something that you always try to bear in mind here. You know, you can use a different, basically, set of language to describe things. In terms of the evaluating of this triple integral. Okay. So now we're not going to evaluate using x, y, z. So yes. Oh, it's interesting. Actually, it's on. Okay, so in terms of evaluating this triple integral here, I'm not going to evaluate using x, y, z. And what that means is basically we're going to transform all of the x, y, z into r theta z. Okay, so basically here is your x will be replaced with r cosine theta. Here's a y replaced with r sine theta. And z, no replacement, is still the same because z is still z. And this dv here, it used to be basically dx, dy, dz, or any combinations. And now it's going to be dr, d theta, okay, and dz. Okay. So the question here is, okay, I'm going to put a question mark right here. We'll find it out. We need a scaling factor here, okay, because this is a small volume differential. And this volume differential is in the xyz plane. And similarly, there should be a volume differential. You can construct that in the r theta z plane, okay, r theta z coordinate system. So there's always a transformation basically factor or scale factor here relating these two volume differential. So that question mark, if you recall that, we can find this question mark using the Jacobian, the determinant Jacobian matrix set here. So if you look at the connection between the polar and the Cartesian coordinates, which is x equal to this, y equal to this, z equal to this. So let's find a question mark here. So we can construct the so-called transformation vector, okay. Basically a transformation vector function. So let's call it t. So t consists of x equal to r cosine theta and y equal to r sine theta, okay. Right, so let me write it maybe a little here. So x is function r theta z. Y is a function r theta z. And the z is also a function r theta z, but it's just a z here. So that's your transformation vector function. And then you can use this transformation vector function to construct your Jacobian here, right? Your Jacobian. So construct the Jacobian, because this is a 3×1 vector, and then you can construct the Jacobian here, which is basically partial x or partial r, partial x, partial theta, partial x, partial z, okay. And then here is partial y over partial r, partial y over partial. Pardon me?
Is it r sine theta for y?
Sine theta, yes. The sine theta is for y, right? Yeah. Yes. Sorry. Good. So you can construct your Jacobian 3×3. Okay. So that's your Jacobian matrix. And we have our x, y, z functions, which is here, here, here. So plug it in. Let's say the first one here will be cosine theta, and then here will be negative r sine theta. X has no z there, so it should be 0. This is r, here's sine theta, here's r cosine theta, and 0, and 0, 0, 1. So that's your Jacobian for this polar coordinate transforming from Cartesian to polar. Okay, so then, as we know from a previous lecture, this question mark here, right? This question mark basically is equal to the determinant of this Jacobian matrix, and then you can add an absolute value to that results. Okay, so that's going to be our the question mark, the scaling factor at here. Okay, so here's your Jacobian, and then we calculate this determinant. That is because the very special matrix, the last column, the last row here. Okay, there's only one element, 1 in here. So the determinant basically is the determinant is 2 by 2 times 1. Okay, so the determinant of the Jacobian, okay, will be basically equal to R. Okay. And R, if you look at definition of the R for the polar coordinates, so R is always the distance from the origin to wherever the point in the xy plane. So R is naturally a positive number, right? Yeah. So basically, you don't really need an absolute sign because this is always basically greater than 0. So what does that mean? Basically, the question mark here is just R, right? So that's just R here. So now your triple integral, okay, is basically R dr d theta dz. Okay, so this is basically the triple integral for under cylindrical coordinates. Okay, so this is in cylindrical. Okay. For this transformation here, this R, you can also derive that instead of using Jacobian, you can also use in previously I think I illustrated. You can try to find sectioned small volume in the 3D space by drawing lines in the direction of the coordinate axis direction. Okay, so you can take a look at lecture notes. You can also get that, but otherwise, okay, very simple, right? So compared to the polar, not much change. You just added one additional variable dz added here. Okay. So when do you use cylindrical coordinates then? It's hard to say, but typically when you're dealing with cylindrical type objects, then you use cylindrical coordinates. But not necessarily cylindrical type of object, but as you can see in the next example, anything actually to do with some sort of there's circle involved in the for the region, okay, and then the cylindrical coordinates probably works better than the Cartesian coordinates. Okay, so let me show you an example here. Let's see, what do I mean in here? Okay, so we'll give you a region D. Okay, so region D is sandwiched by two surfaces. Okay. Here are the two surfaces. So these are the two surfaces we're sandwiching this region D at here. This is the scale that you have to have now. I mean, we're not talking about a very sophisticated object or surfaces that are here. So when you see this, it should strike you right away. Like the first one here is a paraboloid, and this is also a paraboloid, except that it is an inverted direction, right, upside down. Okay. So in this case here, first step is always try to sketch. Okay. Try to sketch out this region D here using the given surface. For z equal to x squared plus y squared, that is a paraboloid pointing up. Okay. And then for the z equal to 4 minus x minus y squared, okay, and this is a paraboloid pointing down. Now this one here, apparently you can see the z has a maximum value of 4, so you can start from somewhere. Let's say if this is 4 at here, you can see, call it this is 4, but you're gonna draw upside down paraboloid now, right? Okay. So that's basically like two balls on the top of each other. Okay, and then this two surfaces will give us this region D. Okay. Is that good? Yeah. And then you can try basically. This is also a good part, and then it's actually useful for us to find the limits. So you can also try to draw the intersection between the two surfaces. Okay. I will show you how to get the intersection, but bottom line, you get the intersection of the two surfaces is actually a circle. Okay. Yeah, it's actually a circle. So I'll show you how to get this circle here. Okay. Yeah. So anything between this green color and the blue color here, that's your region D. Okay, it's your region D here. Okay. So let's say for this question here, let's say what's the volume of this region D? Let's calculate the volume of the region D here. Okay. To calculate the volume of the region D, hey, we need a number of things basically to calculate this one here. Let's see, if I haven't learned cylindrical coordinates, actually the first thing jumping in mind probably is to use Cartesian coordinates, because there's no cylindrical really type of objects involved here, right? Yeah. So let's just try this Cartesian coordinates first, okay? Yeah, if we try Cartesian, then what do we do? Okay. So for Cartesian coordinates, number one step, you sketch everything, okay, and then you build it. Basically, you will try to determine the order of integration. Okay. So let's say I will try to determine the order integration using dz, dy, and then dx. Okay, so let's see, we use this one here. Okay, this is the order I'm going to do it. If this is the order we're going to do it, then the next step is you need to sketch the shadow of the region D in which plane? In which plane? In the xy plane, right? So if you project this whole region D into the xy plane, and you will get a circle here. So I'll show you how to get the circle now. So basically, you're going to get a circle in the xy plane, and that circle is basically this intersection area, intersection curve between the two surfaces. So this is your shadow here, okay? So how do you get this circle here? Apparently the circle represents the most outer edge for the region D, and this circle is the intersection between the two surfaces at here, right? The intersection. So if you look at the intersection at here, here's the two curves. Yeah, here are the two curves here. So intersection between this and this. Okay. So how do we get the intersection curve? Intersection basically means at that location, all the z value at here is actually the same, because see, the z is the same thing here. So all you need to do is substitute the first z into the second z. Okay. So you get this equation at here. A little bit of simplification, then you end up with x squared plus y squared equal to 2. Okay, so basically that's the circle, right, with a radius of root 2. Okay, yeah, good. Now we got our shadow at here, and then we can go ahead to find the limits for z, for y, for x, right? Okay, so the limits for the z, I'll just quickly show you. You starting from the shadow, any point within the shadow, you draw basically. You can draw an arrow line, okay, go through that point, okay, and then go through this region D. the lower contact, so first contact, second contact give you Z mean and Z max, and apparently the first contact is at the bottom surface, and the second contact is on the top surface. So your Z mean is x squared plus y squared. Your Z max is 4 minus x squared minus y squared, right? Okay, so I will just simply write down this integral right here. So volume, basically you're integrating 1, okay, and then it's v, here's a dz, dy, and dx. So your z here mean is x squared plus y squared. Your x max, z max is 4 minus x squared minus y squared. Okay, that's your z limits. Your y and x limits, then you need to find that using the shadow. And then this one here, basically you need to find it by drawing the reading lines across the shadow. Your sorry, it was telling me it was polar. To find the y and an x, so you need to draw a arrow lines in the y-axis direction. Okay, so your y-axis direction, first contact is on this half a circle, second contact is on this half of a circle. Okay, yeah. So basically your y mean is what? A negative 2 minus x squared. Here is a positive 2 minus x squared. Okay, that's your y mean, y max. Finally, x mean, x max. You sweep this green arrow lines from one edge to the other edge, and basically from negative root 2 to positive root 2, right? And that's your x mean, x max. Okay, so there. This is your basically volume here, right? In terms of Cartesian coordinates. And honestly, I don't even have to go through these steps here. Just by looking at all the square root, all these squares here, you would anticipate it's going to be a very challenging integral to solve. Okay, yeah. So this is actually basically tells us the Cartesian coordinates out here not going to be very friendly. Okay, so let's look at the cylindrical coordinates. Okay, so if I use cylindrical coordinates, and how does it look like now for yes?
Is that bottom limit negative root 2?
Oh yeah, where did that go? Okay. Okay, yeah. Is that clear? So let's look at the cylindrical here. Okay. For cylindrical coordinates, you also have to decide on the order of integration first. You do have 3 variables, right? You have what? You have r, theta, z, 3 variables sitting here. Okay. Yeah. So decide on order, okay, of integration. Now this one here, typically, okay, literally, theoretically, you can actually use in any orders. You know, basically r theta z, theta r z, or z r theta. You know, any combination theoretically. Okay, but often in time, this dz, dr, d theta, this order, okay, usually works for maybe over 90% of the type of questions here. So I'll show you how each one demonstrates different orders later, but most of the cases, and you probably will use dz, dr, d theta as this order of integration. Okay, yeah. So I'll demonstrate if I use dz, dr, d theta, then what's the procedure to find the limits for z, r, theta, right? Okay. So let me redraw this region in here, just not to confuse with the Cartesian coordinates. Okay, that's the region that we're talking about here. Okay. So here's a z equal to x squared plus y squared. Here's a z equal to 4 minus x squared minus y squared. So when you looking for the z limits, here, okay, what you need to do, well, actually, before I find the limit z limits here, okay, just a second here. You actually will do the same, very similar procedure here, because we decided to do the z. So we still need to draw the shadow of this object, okay, of the region D. We still need to draw the shadow, because the r and the theta are determined by the shadow. Okay, so sketch the shadow. It's still in the xy plane, because in this case here, the r and theta is basically still determined by this x in the xy plane here, because this is x r theta is the xy plane. Okay, so once you finish the shadow, sketching the shadow here, then we can start to find z limits, because z is the first variable we're integrating with. Finding the z limits, very similar. You're starting from any point inside this shadow, then you draw a arrow line, okay, through that point and through this region D. Okay, right? Just like a Cartesian, isn't it? Right? So you draw in the z-axis direction, okay, and your first contact will give you z mean. Second contact will give us a z max. Okay, but we're not going to use Cartesian coordinates, right? Okay, we're not going to use Cartesian coordinates. So first contact, you know that it's s squared plus y squared. So what do we do is x and y? Replace that with r cos theta, r sin theta, and take out the r squared factor, then the rest of them becomes 1. So that's just r squared. Second contact is 4 minus x squared minus y squared. Same thing. Replace xy with r cos, r sin. So this will give us what? 4 minus r squared. So now this is basically everything is consistent, right? You're purely using polar coordinates, cylindrical coordinates. Okay. Yeah. So that's your z mean, and this is your z max. Okay. Yeah. To find the r and the theta limits, so I'll just put them together here. Okay. And that's where you focus on the shadow. In the shadow, you draw arrow lines, reading lines, okay, out of the origin, okay, across the shadow, just like you're doing with the polar coordinates now. Your r mean is the first contact, r max is the second contact, and this is a circle we're talking about here. So r mean is 0, and r max is the radius, and we just find the radius in the previous step, which is the root 2 for the circle. Okay, so that's your r mean, r max. And then theta mean, theta max, basically you need to sweep these reading lines across the whole shadow, which of course is 0 to 2 pi, right, because it's a full circle here. So now everything is here now. Your volume in terms of this cylindrical coordinates, it will be r squared here, 4 minus r squared, and then this is your r limits, this is your theta limits. Okay, so first you do the dz, then the r, then the theta. Okay, so don't forget this small r here, right? That's the scaling factors for cylindrical coordinates. Okay, so this will be a much easier integral to evaluate than that triple integral in Cartesian coordinates. We can quickly try this here. This is 0 to 2 pi, 0 to root 2. So you have z here, which is 4 minus r squared, right? Upper limit minus lower limit, then r d theta. Okay. So here's 0 to 2 pi, okay? And then here's 4 minus r squared times r here, so that's basically 4r minus 2r cubed dr d theta. So here is always a little bit shortcut because you see the inner integral has nothing to do with theta, right? So basically, there's only the outer integral here that matters for the theta here. So you're going to get a 2 pi for the theta integration, and then the rest of them basically is the results of the inner integral here. So that's pretty straightforward integral here. Okay, and this resulted here in terms of 2. So the overall 4 pi. Yes.
Is there an actual function in the integral, like for z, dz, r, dr, would you change that to would you change that to cylindrical to integrate, or would you just leave it the way it is?
Or if you have a z here, you mean?
No, if you have like, like 4z or z cubed or something.
For example, if I have a z as an integrand, I'll keep the z.
Oh, you just integrate around it?
Yeah, because this is your z, right? Is one of the integration variable. Yeah. Okay, good point. Yeah. Any questions on this part? Right. So yes, Eric. Yes, typically you will. Yes. Well, unless the edge at here is not a significant, really the edge. It's right. You mean the edge is actually inside? Then that's not the edge, right? The edge is the actual, the most outer boundaries. Yeah. So if this edge is somehow, I mean this is not edge, but if this intersection somehow is included by another edge, then we don't really have to sketch that. Okay. Okay, so that's cylindrical coordinates at here. Okay, yeah. So before we move on here, let's take a look at a couple more examples. Okay. So there is a shift of mind always at here between the Cartesian cylindrical and then the next spherical coordinates. So I'll show you another one here, just to establish a connection for the same object, the connection between Cartesian equation and the cylindrical equation. Another very typical object we deal with is called a cone. So the cone at here, essentially, we're looking at an object like this. Okay, so and it could be a cone pointing upwards too. But this is a cone here we're looking at here. Okay, so a real part of the ice cream cone, like this kind of thing. The cone in Cartesian. Okay, in Cartesian coordinates, it's z equal to this. So this is one equation. I'll show you a couple different ones here. But if you see a z equal to root x squared plus y squared, and this is basically is a cone, a shape like this. Okay, so with the tip of the cone right at the origin. Okay, so when x, y equal to 0, you get the z equal to 0, right? Okay, so this is a cone. As a matter of fact, for when you put a constant in front of the root, in front of the square root, okay, and that's a general cone. Okay, yeah. So a cone could be this, and it could be this, right? You know, yeah, it could be this. So it's different, but you know, when you buy ice cream, you want it to be this, right? Yeah. So, and that number a at here, okay, determines, so basically the slant angle for the cone at here. Okay, so this is number a. So let's look at this equation in here. So I'm telling you this is a cone in here now. So then let's kind of reverse, basically work it back. Why this is a cone, and also I want to answer it here is, how about the cone in cylindrical coordinates? Okay, so let's answer this question here, and then we'll actually see it a little bit. So later we'll also look at what's a cone in spherical coordinates. Okay. Yeah. Cylindrical coordinate basically means you're not going to use a z, x, y. You're going to use r, theta, z to describe this surface at here, right? Yeah. So how do we do this then? It's actually quite simple. I mean, all you need to do is you need to replace x with r cosine theta and replace the y with r sine theta. Okay. So let's do this replacement. If I do this replacement here into this equation, so what do we get for the z? Here, here. Do a little bit of simplification. Your z equal to r, right? Z equal to r. Okay. Now that's very simple. Z equal to r. Give us a cone. Okay. So let's interpret this a little bit here. What does z equal to r mean, right? Here's how we can interpret. Let's pick a point on the cone. Okay. Any point on the surface of the cone right here. Then I'm gonna drop this point. Okay. Project that point to the xy plane. Okay. Yeah. So if this is the point on the surface of the cone, and then definitely that point has a z coordinates, right? Has z coordinates. And when you project this point to the xy plane, and then you connect the origin to that projection in here, this is your r, right? This is your r here. Okay. So what this equation, what this Cartesian coordinates tell us is a z equal to r. Basically, you look at this connection in here. So this guy equal to this guy. And another thing you can imagine is you can always do what? You can always connect the origin to the points, right? To the points. Okay, you can always connect the origin to the points. So if you have a cone surface, you can always connect the origin to any point on that surface. So you can imagine you can construct really as many of these kind of edges here, right? Okay. Now, what you see it here now, basically this is Z, this is R, and you have essentially you have what? You have a right triangle here, right? You have a right triangle here. So that right triangle here, it basically looks like this. Okay, so this is your Z, this is your R. So my drawing is not R should be equal to this. So this is your Z, this is your R here. Okay? Yeah. So Z equal to R, meaning what's the angle here? 45, right? Yeah. So that cone, okay, if you draw a point from origin to any point on the surface, guess what's the angle between that edge line and the z-axis? What's the point? What's the angle between this red line and the z-axis? 45, right? It's 45 degrees. So this is basically what the z equal to r tells you here. And as we learn next for spherical coordinates, so this angle here will define it as a phi angle, okay, as a phi angle. So basically, you see, what's the commonality for the cone surface here? Z equal to r. You can also see what? Phi equal to 45 degrees, right? So when you have a cone which sits at 45 degrees, you can just literally just say phi equal to 45 degrees represent a cone. Okay? Yeah. And that's actually what we're going to cover next for spherical coordinates. So this is the alternative way of describing a cone here. Okay? Yeah. So this is your interpretation of z equal to r. Now, how about let's give a different cone here. So let's just give you a different cone. Z equal to 1 over root 3 square root x squared plus y squared. Okay. Now this is a different cone now, right? Because this coefficient here is not 1, it's 1 over root 3. If I use a similar approach, then we get z equal to 1 over root 3r, right? Okay, so that's your still the cone equation, but this is the cone in cylindrical coordinates now. Now, can you tell me what's the phi angle at here for this particular cone? What's the phi angle for this particular cone here? So z equal to 1 over root 3 r at here. This is your phi, huh? This is your z, this is the r here. So if I draw it, it makes your mind. So this is a z, this is r, and this is your phi at here. So phi equal to what? Tangential phi equal to r over z, right? So r over z, and in this case here, r over z will equal to root 3. So it should be what? Pi over 3. Okay, 60 degree. Yeah, my drawings doesn't make sense, but yeah. So now you can literally basically consider if you have an arbitrary number, okay, before this square root, okay, before this square root, then you end up with a z equal to just a times r, okay, a times r, and you can calculate the phi angle accordingly, right? Yeah. I'll come back to this cone when I cover application of triple integrals here, okay, and you'll see how this actually will be made use of to evaluate triple integral using cylindrical coordinates. Okay. Any questions on this part? Yeah. Okay. So next one, I want you to exercise just very quickly here. See now if you get the hang of finding the limits for cylindrical coordinates. Okay. So here's a region D. Okay. Region D is sandwiched by two surfaces. One is x squared plus y squared equal to 4, and the other is z equal to x squared plus y squared. Okay, so and I should put actually another one, xy plane here. So three things to give this region D. Okay. So try to sketch this first. Try to sketch this. See if you can imagine what type of region we're talking about here. Yes, you can. Yes, you can. Yeah. I think you can. Yeah. Yes, you can. Yes. Yeah. It's basically integration by pieces. Addition.
Since when you're on the xy plane, x and y
That's integration. Sometimes it's easier to draw a quarter of the region instead of doing whole region. Alright, so you're able to sketch this thing out? Yeah. First of all, when you look at the x squared plus y squared of 4, and that's not just a circle, right? Oops. So that is not just a circle. That's actually a cylinder. Okay, it's a cylinder. So, okay. And then xy plane, it's just xy plane, of course. And then z equal to x squared plus squared, and that's the paraboloid we have been talking about all the time. Okay. So now three things together. So what are we looking at? We're talking about a region above the xy plane, below this paraboloid, and also bounded by the cylinder here, right? It's within this thing here. Okay. Yes.
So are we just assuming from this question that the function of x, y, z is that's why it's the code?
Oh, you mean this one here? Well, yeah, because you have to now visualize everything in 3D space. So when you have x squared plus y squared of 4, so it's a circle, right? But this circle basically what they describe is a cylinder with the infinite top and the bottom boundaries. Yeah, because there's no z limits at here. Now sometimes, right? Sometimes you probably will see, okay, here is a cylinder, and then you put a z boundary saying z goes from 0 to 3, for example, right? So that you can imagine it's chopped off at 0 and 3, so it's a part of the cylinder now. Okay, yeah. Okay, so if this is the region D at here, okay, and now you're supposed to, let's say, integrate any kind of function. Okay, any kind of function here. So what I want you to exercise now is, can you find its limit, okay, but using cylindrical coordinates. So we don't need to calculate anything, just find the limits. The order of the limits, let's try the same thing. dz, rdr, and d theta. Okay. Yeah. Find the limits of z first, then limits for the r, and limits for the theta. Okay, for the z, meaning you go first sketch a shadow, which is a circle here. Then you go up, up, up through the boundary. First contact, second contact. Right? That's your z mean, z max. Z mean is quite easy. Z mean is 0. Z max, which is on the top surface, the paraboloid. So it's x squared plus y squared. But you don't use x and y. You use r and theta. So replace x and y with r cos arc sine. So basically you get z equal to r squared. So upper limit for the z is just r squared. And now you draw a reading line out of the shadow. First boundary, first contact point give you r mean, which is 0. Second contact give you the r max. Well, this is where you had to be careful. So what's r max? R max is the radius of the circle. But then what's the radius of the circle? Apparently it's the radius of the cylinder at here, right? So which is 2. Finally, the theta, sweep this reading line 360 degree. So 0 to 2 pi. Okay. So this is how you find all the limits for z, r, and theta. Okay. Okay, so far what I have exercised or showed you, demonstrated, is always the order Z R theta, right? Now what about, let's say, a different order in integration? So how about, let's say, dr dz d theta, right? This is not saying that you have to do this way, huh? It just sort of to demonstrate if I change the order, then how do I find the limits, basically, in terms of this this new order right here. So what I want you to establish this concept here is the order integration. It doesn't really matter what order is. Your objective is what? Your objective is to sweep through this region D, right? That's what integration is about. You're integrating through this region D. Basically means you're trying to sweep through the region D or to recreate the region D without redundancy, like what we did in the double integral. So if I do r theta here, so let me use the cone as example here, okay? Let me use the cone as example. So let's say this is a cone right here, right? This is the cone. Maybe let's start with the dz dr d theta. Let's see how do we sweep through the cone or recreating the cone right here. How do we do that? We starting from the within the shadow, we go up. So then we basically from first contact, the second contact. So the first step, when you sweep this along the z-axis, first step, what do we create? We create basically a line segment here, right? And the second step is the R. When you do the R, basically you draw the arrow line, reading lines here. So now the second step, what really happens is what? It's like you move this line here. Move the line in which direction? In the R-axis direction, right? So I draw it here. Basically, I should move this direction. If I draw it arbitrarily in another location, I should move an arbitrary direction, right? So in this case here, if I move in the R direction, the second sweep, what do we create? We create this triangular cross section, right? So you basically you move from R equal to 0 and then all the way through this shadow, basically up to this edge here. And then last step, you sweep around this shadow, the theta. In this case, it's a 360 degree. So basically, it's like in AutoCAD, you do a sweep, right? Then you created this region D. Okay, right. So that makes the region D, and then you're not redundant. There's no redundancy here. So what about the dr d theta dz? Let's see, can we follow a very similar line of thinking in here? Okay, so if you do dr dz d theta, then your first step, the line that you draw, or the first sweep direction. In this case here, you're sweeping along the z-axis, right? So in this case here, if I'm going to sweep now, I'm going to sweep in which axis direction? In the r-axis direction. And the r-axis direction basically means, let's say you're going to start from anywhere inside the region here. You're going to sweep, let's say, in this direction. This is r direction here. Okay, so you draw a reading line. Okay, you draw a reading line, and then that's your r-axis direction, arbitrary. So your first sweep, you end up with this little line segments here. That make sense? Okay. Second one, you're going to sweep this line segment in which direction now? In the z-axis direction. So now you move this line here basically from bottom to the top, right? So similarly, you created what? You will create a cross section like this. And finally, you sweep this last one 360 degree, and then you get this the region D here. Yeah.
For this object, is the shadow just the circle that you see on the on the bottom?
For this one here?
Yeah. Is the circle just the shadow that you see?
Yeah, this one here, the shadow actually is not quite meaningful now, because see here, I can draw the shadow in r theta, which is the circle here, right? Yeah, but for this one here, then the shadow should be in the z theta. But then what's z theta? This is not very intuitive as like xy plane or zy plane, right? So in this case, you actually don't really need to think about the shadow anymore. Okay? And then you can just simply look at the actual object to figure out the limits. So for example, the first drawing from here to here, your r starts at 0 and then end up at any point on the surface here. If I use the same cone here, okay, so which is z equal to r, right? So basically, what's your r mean? Your r mean is 0. Your r max is z, exactly, right? The top surface, exactly. That's right. Yeah. So this is going to be numerical value, maybe 4 or whatever. Yeah. Yeah. Okay. Theta is just theta. Yeah. 0 to 2 pi. Okay. Very good. So that's the idea, to sweep through the region or to recreate this region here. It's like a manufacturing process, right? You know, you could 3D print this line here first, and then you do the rest of the work. But anyway, right? So that's the point here. Okay. The tricky part is d theta, dr, and dz. Okay. Think about this d theta, dr, dz. Okay. And how do we basically recreate the region D using this order here? Okay. So here's a cone right here. Okay. So I'm going to use the order theta rz, right? So if you use theta rz, then we're going to start anywhere inside the region now, not the shadow, anywhere inside the region and here, okay? So theta basically means you will draw or sweep in the theta axis direction, right? Theta axis direction. For cylindrical objects, right? So let me go back to the first one here, all the way to the top. If you recall that in the previous lecture, I draw this is your z-axis. Here is your r-axis, right? Because this is your direction of r reading direction. And theta is what? Theta is always a direction perpendicular to R, and that's the rotational direction, right? Yeah. So now if you go back to this question here, so what we really can do is we can actually, basically the first step is to create, okay, a very, very small circle, okay, inside the region D here. So that's the first step basically. Can you imagine that? Right. So inside in the cone, you create a circle. That's basically sweeping around the theta axis direction. Okay? Yeah. And then what's the next step? It's R, right? So that circle will go from the z-axis all the way expand to the edge of the surface of the cone. So when you expand everything up, you end up with a part of the cross section at that location, right? Yeah. And finally, you move this cross section up and down to create this cone right here. Okay, that's your z limits. Okay, yeah. Yeah, theta 0 to. That's right. Yeah. For this case, yeah. Okay. So just to give you an idea, if you choose a different order of integration, and what will be the implication for finding the limits at here, right? Yeah. So whichever that's more intuitive to you, and then you should use that order. Huh? Yeah. That the limits. Which one? The last one here. Yeah. So let me redraw this here. So this is your step 1 here. So theta goes from 0 to 2 pi, right? And then step 2, use a different color. Step 2 is to expand that circle, okay, at that one cutting location, and you end up with this. So your R 0 to, in this case, this is still the same cone here, okay? So z equal to r. So the r equal to 0 to z. Finally, your z, you move this green disk, right, green circle from the bottom to the top to scan through this whole region D. So that's 0 to, let's say this is a 4 here, okay, to 4. The cross section, top cross section is, just for example, z equal to 4. Okay, yeah, there's a top plane here. So that will be the limits, right? For example. Okay. Yeah. Does that make sense? Yeah. Okay. So if I find most people are more comfortable with dz, dr, d theta, okay, to sweep through the region D. Okay. There are maybe just very special case sometimes you choose different orders for integration. Any questions so far? Oh, good. Okay. So let's look at the last type of coordinate system. Evaluating a triple integral in spherical coordinates. Okay, spherical coordinates. So spherical, by the word meaning, it means is you have a sphere. So basically means if you have a region D that's actually a sphere type of object, then chances you're going to use these spherical coordinates to evaluate this triple integral. Okay, yeah. So let's introduce this spherical coordinates first. Okay, so here is a point P in the 3D space. Okay. To define these spherical coordinates, you also use 3 variables. The 3 variables defining the coordinates here basically is you connect the origin with the point P, then the distance from origin to that point P is denoted as rho. So this is one spherical coordinates here. And the angle from the z-axis, to this OP line vector right here is defined as phi angle. So this is the second spherical coordinates. And then you project this point P to the xy plane and connect this projection point to the origin. And then you draw the angle from the x-axis to the line at here. That's your theta. So rho phi theta is the set of spherical coordinates. Okay, so set of variables for spherical coordinates. So rho phi theta. So theta seems not so strange to us because we have seen the same theta in the polar and also in the cylindrical coordinates, right? Yeah, so that's fine. The rho and the phi are 2 basic new variables we never seen before, but it's quite easy to understand. Rho just represents the distance from origin to the location of the P. And phi is the angle from Z to OP. So this is important, huh? The definition of the phi, the angle is from the positive z-axis to OP vector. It has to be like that. Okay, it's not from OP to Z. It has to be from the z-axis to OP. Okay, so that's rigidly defined as the phi here. Okay. Then the rho here, you see. Before we talk rho, one more thing about the phi angle here. So if you look at the phi angle here, right? If you pick a different point P, maybe if you pick a point P below the xy plane, then the phi will be greater than 90 degrees, right? Yeah. So there is a limit rigidly set for the phi. It's going to be always between 0 to pi. So maximum value for the phi is 180 degrees. So there's a reason for that. I'll show you why. But for now, the phi angle has to be always between 0 and pi degree, okay, 180 degree. So that's the very rigid part for the phi at here, because this is constrained by the way that we're sweeping through the region D or recreating the region D at here. Okay? Yeah. And the rho at here, as I said, it's the distance from here to here. So technically speaking, rho just basically equal to x squared plus y squared z squared, and then you take a square root. So rho is naturally greater and or equal to 0. Right? That's your rho at here. Okay. So this is a spherical coordinates. Basically, you can imagine at this point at here, you can construct a different set of coordinate system. So if I need to construct spherical coordinate system, then just like the x, y, z Cartesian coordinate system, we draw basically a E rho. Okay, this is in the rho direction. Okay, this is in the rho direction here. You draw an axis. Okay, in the rho direction, and then you draw another one in the phi. What's the phi here? Phi is perpendicular, so it should be this direction here. Okay, perpendicular to this. That's your rotational direction. And then the theta is in that direction here. So theta. Okay, yeah. So that construct to get all together. There's this spherical coordinate system. Okay. Yeah. Okay, so what's the connection between spherical coordinates and the Cartesian coordinates? It's actually quite straightforward. If you look at the geometry at here, right? If you look at the geometry, this is your x, okay, this is your y at here, okay, and this is your z at here. So it's very straightforward. You look at the connection. What's the x distance, okay, in terms of rho phi theta? So I can do this calculation. This is phi, and this is also phi, and this is a right triangle here. So that's a right triangle. Okay, so your rho is the length of the hypotenuse at here. So basically, for this section here is what? Rho times sine phi. Okay. Here's a theta, and then times cosine theta. So that's your x equal to rho times sine phi times cosine phi to get x here. Similarly, your y will be rho times sine phi, get this part, and then times sine theta. And finally, your z is this portion here, and that's rho times what? Cosine phi. Okay, so that's the connection between the Cartesian coordinates and the spherical coordinates at here. Okay, yeah. Okay, so before we move on to the triple integral here, so let's take a look at just to establish a concept for spherical coordinates at here. Okay, yeah. So if I write down a Cartesian equation, for example, I have a Cartesian equation like this one. Okay, so can anybody tell me what does this equation represent? What type of shape is this thing? It's a sphere. Where is the origin of the sphere? +1. The origin is a coordinate. 0, 0, 1. Right? Very good. That's a sphere at origin at 0, 0, 1. So 0, 0, 1 is over here, and the radius of the sphere is 1, right? So square root of 1. So you can draw, basically you can draw a sphere. Okay, here's a 1, and then the top here is 2. So that's a sphere, right? This is a sphere. Okay, yeah. Okay, so now if I wanted to write the same sphere, but not using Cartesian coordinate, but instead using this cylindrical, using the spherical coordinates. Okay, yeah. Then what's the equation or expression for this same sphere in spherical coordinates? So what do we do? It's actually quite simple. It looks simple, but it's a little bit complicated at the beginning. So you will substitute the xyz expression at here into this Cartesian spherical equation. Okay? Yeah, plug it here, here, here. And you will have to do some simplifications here. So let's try it, huh? The x is replaced with rho square sine phi square cosine theta square. And the y is replaced with rho square sine phi square cosine sine theta square. And the z is replaced with rho cosine phi minus 1 square equal to 1. Okay, right, that's the replacement. Okay, looking at the first two terms here, what's the common factor? It's rho square sine phi square, right? Once you take out the common factor, that you're left with cosine theta plus sine theta square, which is 1. So that's it, right? So you basically get the rho square sine phi square. And now I will expand this bracket. Okay, expand the bracket here, so that gets rho square cosine phi square minus 2 rho cosine phi plus 1 equal to 1. Okay. So the first two terms, common factor rho square and sine phi plus cosine phi, and then another 0, right? So you got a rho square here. And this one cancel. So you get 2 rho cosine phi equal to 0. Take out the common factor rho, so rho minus 2 cosine phi equal to 0. So for this one to be 0, you either rho equal to 0 or rho equal to 2 cosine phi. But rho cannot be 0, right? Because you're talking about sphere. How could the rho be 0? So the only possibility is rho equal to 2 times cosine phi. You see that? For the same sphere in spherical coordinates, it's actually quite short, right? So it's just rho equal to 2 cosine phi. Okay? Yeah. That's the equation in spherical coordinates. Is that good? Okay. Okay. So I want you to exercise this one before we go, huh? I'll let you go here. Actually, I have another one. Try this. Try this. Can you start from anywhere? Okay. Start from origin. Then you draw any direction. Okay. Draw them in the direction, in the rho axis direction. So you will inevitably bump into the surface of the sphere, right? Okay. Now, from here to here, so technically speaking, from here to here, that's what? That's the variable rho, isn't it, right? That's the rho here, representing the distance of that point. And I want you to connect this point to the top edge at here. And guess what? It's a right triangle. Okay? So because it's a sphere, so anywhere you draw, bump into the surface of the sphere, it's actually part of this, it's a big circle here. And what's this angle here? This is the angle according to our definition. That's the phi angle. Okay? That's a phi angle here. So now, then what is this distance? Right? This distance at here, from here to here. What does that equal to? Using this right triangle. It's what? This side is 2. Here's the phi. It's what? 2 times cosine phi. That's exactly what we just derived here, right? Okay? Yeah. This is actually part of the necessary part of work process to find the rho limits. Okay? The rho limits here next. Okay? Okay, last one here, really last one here. So, let's say I have a cone here. Okay, this is the cone equation. What's the cone equation in spherical coordinates? So what do? You basically replace the z with rho cosine phi. Replace the x with rho sine phi, cosine theta, and the same thing for the y. Okay, yeah. So simplify this. You're gonna phi equal to pi over 4, like what I just showed you before, right? So in spherical coordinates, the cone is just phi equal to 45 degrees. Okay. Any questions? Okay. We'll see you next week. No lecture next Monday, but we do have a lecture next Tuesday. By the way, tomorrow is reading break, and I suppose you should read. So.